As we know, rational numbers are numbers that can be expressed as a ratio. So really, rational square roots is just code for square roots of perfect squares. So let's take the number 25. We know the square root of 25 is equal to 5. However, 5 squared equals 25, and negative 5 squared equals 25 as well. So truthfully, 25 has two roots, two square roots. So that leaves us to some symbols. If you see the symbol that's just this plain old radical sign, it means the principal, and this is not going to be true when we have variables, but the principal or positive square root. If you see this sign, you can imagine it means the negative square root. And if you see this sign, it means the positive and negative square root. So, all sorts of radicals to look at are evident in the experiment, in the example of saying the square root of 100. And granted, that means the principal square root of 100 is equal to 10. We also know, however, that 100 is 25 times 4. When I'm dealing with radicals, if I have that, it was also equal to this. I can separate them into two separate square root things. We know the square root of 25 is 5, square root of 4 is 2, and lo and behold, I get the same answer. This is all illustrating a commonly used fact. If I take the root of a times b, it is always equal to the square root of a times the square root of b. We will be using this quite frequently. Similarly, if I want to know what the square root of 100 divided by 25 is, I could think of that as 100 divided by 25 is 4, and the square root of 4 is 2. That's the other thing that's like this is that I can separate this out to the square root of 100 divided by the square root of 25, and that is 10 divided by 5 is 2. This illustrates the property that if I have the square root of a divided by the square root of b, it is the same as separating them into the square root of a divided by the square root of b. Most of the time that's really, just quite apparent, but let's say I had the problem that said the square root of 12 over the square root of, let me think, what would be a good one? Square root of 27. At first glance, it really doesn't look like we can do anything here, but because neither 12 or 27 is a perfect square, but I can think of 12 as 3 times 4, and I can think of 27 as 3 times 9. So I get the square root of 4 over 9. In other words, I can just reduce the fraction first. And so now I have the negative square root of, square root of 4 over square root of 9, and as we can see, that is 2/3. So the answer to that problem would be negative 2/3. Sometimes the numbers are kind of big. We can say the square root of 225, and many of you know that that's 15. But if you didn't know that, you could do the prime factorization to find what the perfect square factors are. Well, this ends in 25, so I know that 25 goes into it. And there are 4 25s in every 100 and then one more. So we can see here that this is the square root of 25 times the square root of 9, which is 5 times 3, or 15. Let's say I got a really big number and I honestly couldn't see what my perfect square factors might be. Let's say I've done the prime factorization. What you want to do with big numbers is find the prime factorization, and take the square roots of each. Prime. And when you take the square root, it's half the exponents. So if I have, I don't know, let's say the number is 3 to the 4th, I don't even know what this number is, times 5 squared times 7 to the 4th. This is a really big number. I know that it's the square root of 3 to the 4th. The square root of that is 3 squared. The square root of 5 squared is 5. And the square root of 7 to the 4th is 7 squared. Then you can use your calculator to compute that. The point is, once you've done the prime factorization, you can take half of the exponents to find the square root. And that's pretty much what you need to know for this unit.